Welcome back to our series on advanced aircraft turbine modeling. In this episode, we're going to look at the data we got, check out if everything is okay, and implement our lookup table. Let's dive right in!
3, 2, 1, top.
3, 2, 1, half, the Flight Test Engineering channel.
When I first planned for this episode, it should have been an easy one. Plot some graphs straight out of the data that we got from pyCycle in the last episode, show that because at lower altitudes Mach is not constant, of course we are in the speed domain, we got some squiggly lines in the graphs, come to the conclusion then that we needed an interpolating function, go ahead, implement it, plot again, hopefully now with smooth lines, and be done with it. But let's look at the data and see what we got. We have a notebook where we're going to do our first imports, the standard ones, pandas, numpy, matplotlib, and we set the theme to a dark background so it looks nicer in the eye, and set the figure size so that we can have a nice aspect ratio as well. And the first thing we're going to do is read in the data that we got from the last episode, the CF34 DAC V2 that we generated. It took us 34 hours plus to generate this thing. And we're going to just read it straight into a pandas data frame. We're going to call it DF CF34. And now, because we're going to plot many times the parameters, instead of just creating a plot, we're going to create a function to create the plot so that we can call it a few times without rewriting it. So let's call it quick plots, and we're going to pass in the Mach numbers that we want to plot for, the altitude bracket, meaning the minimum and maximum altitude that we want to choose, the power percent bracket, how many power settings we want, the right-hand plot parameters. We're going to have two plots. The left hand is going to be thrust only, and the right hand is going to be a parameter that we choose. And then the data frame that we want to plot from, the DF. So we create two figures, AX1 and AX2, with two subplots, give it a title, and for each Mach in the Machs that we pass in, we create a Mach bracket, because if you remember, our data frame does not have constant Mach numbers. So the Machs are going to be varying in lower altitudes as we plot the points. So if we want to choose one Mach number, we have to choose a band around this Mach number to filter the data from. So that's what we're doing here. We're creating a lower band number given that the Mach that we're choosing, minus 0.01, and an upper band with plus 0.01. And then here is the trick that we get free from pandas, right? We can filter the data frame with the data that we want. So we're going to create here a filtered data frame where we take in the original data frame that we have passed into the function, and we select the altitudes that are higher or equal to the lower band of our bracket, and lower or equal to the higher band of our bracket. And the Mach numbers are higher or equal to the lower band of our bracket, and so forth, lower or equal to the higher band. And the PC, the percent power, same thing. When you do this, you're going to select only the points that you want from the data frame. And then we just dump the data into a NumPy array. In the Y1, we're going to plot the thrust, Fn. The x-axis for the second graph, for the right hand, are going to make it the same as the first one, meaning altitude. And we again choose the y-axis for the right-hand side, given the parameter that we passed in, the right-hand plot parameter. Then we just plot x1 and y1, which is going to be altitude and thrust. And on the right hand, altitude and whatever parameter we passed in. We set the title, we set the X label to altitude, the Y label to thrust for the left hand, alpha just to make the plot a bit nicer. Then we set the title for the right hand parameter, X is going to be altitude again. Then we add a legend with the title for the Mach number in the lower right hand corner. And we show the figure. So when we run this and we choose, for instance, the altitude bracket 0 to 42,000 and the PC power percent bracket 1, because we want to plot 1 power percent only, The Machs are going to be the whole range we have from 0 to 0.9. The right-hand parameter, I'm going to plot gross thrust, and we call the function, and this is what we got. So let me zoom out a little bit just to make it better. And this is what we get when we call the function. We get thrust on this side and gross thrust. This is net thrust, and this is gross thrust here on the right-hand side. And we can see that we have one line for each of the Mach numbers that we selected, 0, 0.1, and so forth. And thrust varies as we expected. It falls as you rise in altitude, and it falls as you increase your speed, your Mach number. But instead of having straight lines, we have some lines that are squiggly, as I said in the beginning. So if we run again the same function for Mach number as our second parameter, we can see that the Mach number is varying in the lower altitudes and it's constant up there in higher altitudes as we calculate it in our deck. And I don't know if you can spot the problem or the anomaly here in this graph. I'll give you a second to try to see that. Yeah, so this is not expected. A sudden bump in thrust at one altitude. We don't know if this is due to the Mach number variation or if it's due to some sort of anomaly in the deck. So to investigate this, what we could do is rerun our deck with finer pitch and maybe run it at constant Mach number for many altitudes. So this is what I tried to do. Instead of running the whole deck for all of the Mach numbers, I chose one Mach number, 0.75, and I ran that from 1,000 to 35,000 feet every 200 feet. And also I ran it with the power percentage fixed to 1.0, which is what we are trying to investigate this. And just to be able to rule out any problems that we might have introduced into our CF34 modification of the original pyCycle example, I reran both. I reran our modified CF34 deck and also the original high bypass turbofan example that they provide in the pyCycle repository. So here we read the two data frames, the DF CF34, which is our modified one, and then we also read the HBTF data frame, which is the original pyCycle deck that they or file that they provide in the pyCycle repository. Again, we define the altitude brackets between 2,000 and 40,000. And also I defined two brackets here and one finer one because we'll see that our problem lies at 19,000 feet. And the Mach bracket is going to be 0.7 to 0.8. We filter the data for both data frames now. And here we are filtering for the altitude and Mach number. Remember, we don't have to filter for the PC because we just chose one. And here we plot the data. This is what we get after all. We see a nice line coming down just as expected for the pyCycle HBTF file that they had at the repository and also for our CF34 deck that we ran. But at 19,000 feet, we see this anomaly here. And if we zoom in to this, we can see that there is something going on with the deck at 19,000 feet. So now to investigate where this comes from, what is the source of this problem, we need to plot all of the other parameters. And we would need to investigate all across our design space for our engine and see which parameter is varying. So to do this, we need to interpolate. We need to create an interpolating function to be able to smooth out the data and try to find where the problem comes from. So let's do that. Let me zoom in. Right, so the first function that we need is a get bracket, meaning that we're going to pass in a target and we're going to pass in a value list. And we want to find what is the neighboring higher and lower values in this list. And notice that the list doesn't have to be in order for us to do this. So we create two lists, the highs and lows, and we check each value from our value list. If it's higher or equal to our target, we add it to the highs. Else, it's going to be added to the lows. And if we detected any of the highs, then our high value is going to be the minimum of those highs. If we have not detected any highs, then our high value is going to be the maximum of our list, meaning that we are at the end of the list. Same thing with the lows, right? If we have any a lows list there, we're going to pass in the maximum of those values. Else, we're going to pass in or return the minimum of our original list. And that's what we return, the low and high values. So the next function here is going to be a linear interpolation, where the classic one. We pass in the number that we want to interpolate for, and then we pass in one pair of points, x2 and y2, x1 and y1. And I know, yeah, the sequence here is not the best, but I already had this function implemented. That's why we're using it again. And we calculate the classic slope of the curve, of the line, and then the intercept, and return whatever point we have at m times x plus x0. Very simple. The next function is going to be the adjust limits function, where we pass in a value, and again a list of values. And this is going to be used to adjust the interpolation limits. So if you give a value in a list that is ordered in this case, if the values are out of range, set the two closest values. This then will allow us to do linear interpolation at the ends of our tables that we calculated for the CF34. So if the absolute value of our value minus the initial value of our list is higher than the value minus the last value of our list, then the high value is going to be the last value of the list, and the low value is going to be the next to last value of the list. If not, then the high value is going to be the second value of our list, and the low value is going to be the first value. Okay, and this brings us to the main function that we want to look at in this episode, which is our interpolate altitude Mach and power setting. We're going to have to do an interpolation in 3 dimensions, and this is what we pass into the function: the altitude in feet, the Mach number, the power setting, and the data frame that we want interpolated from. We're going to call it df. And we are going to pass back or return a dictionary with all of the parameters that we interpolate in between. So the first thing we want to do is identify which are the unique altitudes that we have in this data frame. So we first filter the data frame here with the alt key, and then call the .unique method from pandas. We get a set of altitudes that are unique for that data frame. Then for each of these altitudes, we create a list of Mach numbers. So for each altitude in those altitudes, we filter the data frame for that altitude, and also we filter the data frame for the Mach numbers. And then again, call the .unique method in pandas to get the unique Mach numbers. And this time we're going to pass it to a list. So this is what we have here, to list. And the same thing, we're going to first identify which are the power settings that we have available in our data frame. So we create this PCs list here by filtering our data frame with the altitudes, and then filtering it with the Mach number, and then filtering for PC. And same idea, we're going to get unique and to list. Same idea. Next, we just capture the column names in this list here, because it's going to make it easier. Since we're going to create a dictionary later on, it's easier to have the column names already in the list. Now we need to think about the data that we have in our data frame. We calculated our DAC and we created a huge table, but we don't have all the data we need to choose any altitudes. For instance, if we want to understand what is the thrust at 10,200 feet, and we have data at 10,000 and 11,000 feet, we need to find what are the neighboring points to our 10,200 feet that we want to interpolate at. So that's exactly what we're going to do with this point bracket dictionary. We define a low that's going to have a altitude, a Mach low, and a Mach high value, and we define a high, which is going to be very analogous. It's going to have an altitude, a Mach low, and a Mach high at that high bracket. The first point bracket that we define is going to be the low and the altitude. So what are the values for low and high in our point brackets for the altitudes? We just call our function that we saw before, get brackets, passing in the altitude that we want to interpolate at, HP, and the list of altitudes at that Mach number that we had created just above. Since this is a dictionary, we pass in the keys. So we check then if the low altitude equals high altitude. That means that we are at the edge of the table, okay? And then if we are at the edge of the table, we just dump the keys into a list for the altitudes, we sort them, and then we're going to say, all right, we know we are at the edge of the table, let's adjust the limits by calling that function, meaning that we're going to pass in the altitude that we want to interpolate at, and the ordered list of the altitudes that we have. So if you recall, we're going to see that we are at the end, and we're going to check and pick the two closest points in the database that we have for the altitude that we're trying to interpolate. So this takes care of the edge case. And now we're going to do the same for Mach number. We have a low altitude Mach low, low altitude Mach high, high altitude Mach low, high altitude Mach high. So for each one in this set here, low and high, we check and get the point bracket Mach low and Mach high, again by calling our get bracket with the altitude Mach numbers that we had. And we do the same. If the low equals the high, we're going to take care again of the edge cases. And finally, these are the PCs, the power settings. We only have PC low and PC high in this case. We just get the brackets and then adjust the limits, same idea as we had before. So now that we know which points from the table we need to pick to interpolate in all of the dimensions, now we go ahead and interpolate. So our interpolate points is going to be just a temporary list that will hold this. And if we say, if the point bracket's low altitude is not equal to the high, meaning that we have 2 points, then we're going to do a query in our database for the altitude to be the high and the Mach number to be the high and high Mach number. Same thing for the altitude high, but the low Mach number. Same thing for the low altitude and high Mach, and low altitude and low Mach number. And then we are ready for the interpolation. So we create a temporary list here. And we go now backwards. So we first interpolate the PCs, then the Mach numbers, and then the altitudes. So here we're going to interpolate the PCs. X1 is going to be the low, X2 is going to be the high, and the Y's are going to be the interpolation points, where our interpolation points equals PC, X1 or X2 and X1. So this is how we just filter out all of the points that have the power settings that we want. And then we're going to append to our temporary points the linear interpolation, aiming at the power setting that we want and the 2 data points that we have from our table. And now we're going to do the same with Mach number. So now we create another list, temporary points 2. And for high and low, we create X2 and X1 with the brackets with Mach high and Mach low. And the Y1 and Y2 is going to be the temporary points, but now at index 0 and 2 and 1 and 3, which are the equivalents for Mach high and Mach low at the altitudes. and we just append to our temporary points the interpolation aiming at the Mach number that we want to get for. And last, we're going to interpolate for the altitude. So we have only altitude low and high. So x2 is going to be the high altitude, x1 is going to be the low, and the temporary points that we got up here is going to be the first and the last one. We pass all these data points to our interpolating function, aiming at the altitude that we passed in, HP. And now we just package everything out to output in a dictionary. So our results are going to be a dictionary, and we're going to add into this dictionary the column names for every column name that we listed up there before. The key is going to be the column name, and the data is going to be our interpolating data, IDX, which is the index here. And we return this result. We can do a quick check here. So we say that we want Mach number 0.3, 18,000 feet, power setting to 1, and we call our results. It's going to be our interpolating function. And then here we print whatever values we pass in, and here we print whatever net thrust that we get from our function. And we see that we get 10,105 pound force of thrust at this condition. So now let's plot some interpolated data, finally. We set the Machs that we want to select for. Let's just select everything from 0 to 1.0. Remember that NumPy is open-ended, so it's going to be up to 0.9. The altitude is going to go from 0 to 39,900 feet at every 100 feet, which is pretty fine. And we're going to set the power setting to 1 only. The iData is going to be a set, temporary. So for all of the Mach numbers and for all of the altitudes, we call our function interpolate altitude Mach and PC at those conditions from our data frame. And then if we select the plot key as Fn, for every Mach number in the Machs that we define here, we create a temporary with the data that we had, and we plot altitudes and this temp. Note that this temporary here is going to be our results with the plot key, and the plot key is going to be our net thrust. And this is our beautiful graph that we get now with interpolated data showing that indeed we have an anomaly at 19,000 feet. Right, now that we know that we have an anomaly, we can plot a lot more data to see what's going on. To do that, I created another plotting function here that takes in altitudes, Mach numbers, the power setting, graph plot number 2 key, and the data frame you want to plot for. We iterate through the Mach numbers and the altitudes, and now we interpolate and create our interpolated data for the altitudes and Mach numbers that we want, that we have defined. And if we do a quick check here with Mach number and gross thrust as the secondary plots, first for the Mach number, yeah, indeed we have straight lines, which is what we wanted, versus the squiggly line that we had before. So this is working fine. And for the gross thrust, again, just checking that, yep, we have something that is reasonable. So now I'm not going to run these two cells again here because they take a long time to run, and then create one plot for each of these parameters, considering all of the altitudes and all the Mach numbers that we have available for the power setting equals 1.0. On this cell here, for each of the figure, I save the figure to disk in a PNG format. So let me change my screen here and open the figure so that we can take a look at what's going on. So in this directory, I have all of the figures. We can see here, the first one, we got altitude, which for all of the Mach numbers, they should match, and they do, so no problem defining the altitude. The Mach number, as we saw, they are straight, no problem. Low pressure turbine pressure ratio. Doesn't look very strained to me, especially at 19,000 feet. This is the problem area we're looking at. High pressure turbine power ratio, again, 19,000 feet looks pretty normal. Fuel to air ratio, no anomalies here that I can detect. The PC, which we set to 1.0, constant, normal. The net thrust, both graphs match, which is nice. That's gross thrust. Again, we see the anomaly, but we don't know where it comes from. This is the ram drag. We can see that as Mach goes up, of course, the ram drag goes up, but we cannot pinpoint this to the problem because at low Mach number, we still have the problem. Overall pressure ratio, yeah, we have something here at 30-something thousand feet, but nothing at 19, so it's not the problem as well. Thrust-specific fuel consumption, that's normal. Bypass ratio, no problem at 19,000 feet. This is the fuel flow, yep, it matches because you have more flow, more thrust, you need more fuel, so looks normal. Now here's interesting. This one is interesting because this is the static pressure at the inlet. Flight condition, static pressure. And for all of the Mach numbers, we see this anomaly here at 19,000 feet. And we should not see this. This should be a straight connection here between these points. So clearly this is one possibility of our problem. There might be some sort of bug in pyCycle calculation of the static pressure at 19,000 feet, which then makes sense. If you get an error on static pressure, all of your thrust calculation is going to be wrong. This cascades down to all of the other parameters. So to me, this is the culprit, the static pressure, but let's keep going. Static temperature, okay. Oops, what was that? Oh, that was the burner. So yeah, okay. We have a squiggly line there because at each condition, we have a condition in the burner. Enthalpy, entropy, yep. So this is the situation. We have probably a bug in pyCycle's static pressure calculation at the inlet. And I had to take the decision to keep going with this video instead of investigating first and finding the bug in pyCycle, because I figured that this is a real engineering channel and this is a real engineering problem that you might encounter in your real life. So I decided to keep the video as this, and now we need to find an interim solution so that we can use the deck as with the data that we have. So let's look at that then. Right, we're back in the notebook. So what do you think the solution would be for this situation here? Well, I propose a very simple one. Let's filter out the 19,000 feet data. We saw that it's localized at that altitude alone. We can assume that all the other data is correct. And if we remove the data at 19,000 feet, we have a pretty good chance of having a good deck. So what do? It's really easy with pandas, right? We create a clean data frame by filtering out and selecting only the altitude that is lower than 18,999 and higher than 20,001 feet. That is effectively going to remove all of the data points that are in between. And we do a quick check here. For the same graph that we had up above, for Mach number and gross thrust, we just create the figures, and indeed, now we don't see that anomaly anymore, right? This is the gross thrust here, and this is the net thrust. So that looks to me as a reasonable deck that we can use for the CF34. And we can also do a quick check here for the flight condition static pressure, And yeah, indeed, we can see that we have a nice curve going through the 19,000 feet that we had the problem before, right? I only plot 2 Mach numbers to be quick, but you can see, you get the point here. So now, the last thing that I would like to do here to make sure that our interpolating function works is to check the extremes. And also the out of extremes, and also do a speed test. So, for instance, let's check if we get a good point at low speed and low altitude by setting Mach number to 0, altitude to 0, and asking the function to interpolate. And we can see that the interpolated thrust is going to be 19,186 pound force, and the closest truth data point that we have in the table is going to be 19,153, which is pretty close to what we have. So I believe in this interpolating function at this condition. Then we check for low speed and invalid altitude. So we set the altitude to -10. And remember, we're going to adjust the limits with our function there. And indeed, we get 19,190 pound force, but we have no data points found in the table. We do it for high speed, low altitude. So Mach number 0.5, altitude 0. We get 12,214 pound, and the closest is going to be 12,351, pretty close again. We try extrapolated speed and low altitude, so Mach number at 0.9 and 0 feet. We never calculated that. And we get 8,000 pound force, but no data in our table, which is correct. And then in the middle of the envelope, Mach 0.78, 35,000 feet, full throttle, and we get 5,461 pounds for our interpolated data, and we get a few points that are close, right? Because remember, we have to get a range of Mach numbers that are close to see if we are actually interpolating the right conditions. And we do. 5441, 5441, 5465, and we got 5461 in our interpolated data. Last one, we get high speed and high altitude, so Mach 0.82, 41,000 feet. Same thing, we get 4145, and then pretty close values for our database. And invalid altitude, if we bump it up to 44,000 feet, yep, we get no points from our database, which is correct. And this one, invalid Mach number, 0.93 at 41,000 feet. We get 4,000 pounds of thrust and no points in our database. And the last item I want to touch here is do an API speed test on our function, because that was the whole idea, to create a lookup table, right? We wanted to implement a deck that you could use in your simulation routines, so it needs to run pretty fast. I think you don't need 100 Hertz, and something like 10 Hertz would do it. So let's see how much we get on this computer that I have. It's a really old one, so you will for sure get better mileage than I am getting. So I will do 1,000 iterations for these conditions. I'm going to call this API here. This equates to 46 seconds for 1,000 calls, which means that we can run this roughly at 20 Hertz, which is pretty good. I think I'm pretty pleased with this condition. And you can, at 20 Hertz, you get all of the parameters that you need from the deck: pressures, altitudes, fuel burn rate, SFSC, whatever. And it's a pretty good result that you can use in your simulator. Well, this episode showed us how important it is to do some critical analysis on your data results. We could isolate the probable root cause for the anomaly at 19,000 feet and filter out the questionable data. And now we have a trilinear interpolating function that allows us to query our data for the entirety of our flight envelope. On the next episode, we'll clean up this interpolating function and implement a first-order response time for our engine. See you there!